All right. Hello, everyone. Welcome to Friday. I'm Miss Danielle, and we have our last day of science experiment. Today, we're going to be working with magnets. So the materials you need, obviously, are a magnet. If you have fridge magnets, or if you have some play magnets, or whatever you have around the house, go grab it now. We also need some small metal objects. I'll be mostly using paper clips, but if you can raid the garage for the little jar of screws and bolts that everybody has. We just need some small metal objects, something that you think is going to attach to your magnet. And we'll test it and see if it does. While you gather those, I'll say a few other things, so run and get them now. This science is being presented as part of Middletown Month, which is what we're having this year instead of Middletown Day. So we have a bunch of stuff virtually, like this science. And then we also have in-person sports challenges that have already started this week. So if you missed it, you didn't get to participate in the baseball one, but next week is basketball. And we're selling Middletown Day bags. So instead of going around to all the tables to get all your cool vendor swag, you can come to Poissy Park. And for $5, you get the bag. You get a commemorative township fleece blanket and other goodies from the vendors, like this lovely little notepad from Dogs on the Farm. The bag altogether is $5, and the proceeds are going to the mayor's chosen charity, which is Infinite Love for Kids Fighting Cancer. And the money goes to a good place. If you haven't done WebEx before, there is a chat where if you have any questions or comments as we go along, my co-host, John, say hi, John.
Hello.
We'll make sure that they get to me. He also tells me what you guys can see through the camera and helps out with some of the science. Hopefully everybody's back with some magnets. And if you don't have magnets, you can still watch and try it again later. Magnets are pretty cool things. They are almost magical in their ability to make things levitate, make things move. You can't see these magnetic forces, but they change things. They're kind of like the wind in that way, that they can move things with unseen hands. We're going to start by trying to build a little levitating chamber. I have also learned that this desk is magnetic, so my magnets kind of stick to it. Before we get too far, though,
If that comes in handy or not.
they must have some purpose. But look at this. This is from yesterday's science.
That looks amazing.
Look how cool our crystal tree grew. If you want to see how this was made, you got to check out yesterday's video. But it even grew down the cup.
That is really neat.
Isn't that cool? I don't think it looks like a Christmas tree. It's like some.
It kind of looks like a brush to me, One of those scrubby brushes.
Oh, okay. To me, it looks like cauliflower.
Or strangely colored.
I accidentally hit it a little bit with my magnet, so a few of the little crystals have come off. But all right, let's try and make a little levitating chamber. So I have some bamboo skewers, and we're going to make a triangular pyramid. Skewers, I got a little bit of clay. You could do this with pencils and Play-Doh if that's what you got. I'm going to put a little mound on each node. Keep it kind of stuck to the desk, and to have a little raised area to stick the next skewer into. Play-Doh is probably better because this one almost turns my fingers green.
I
I don't know. It's Crayola.
Oxford. Probably safe for you.
So it does wash off, but it's pretty green in the meantime. And then I have a ball for the top. I need 3 more. Bring them together. This is called a triangular pyramid because it has a triangle on the bottom. The pyramids, like the ones in Egypt, are rectangular pyramids, so they have squares on the bottom. And then we want to hang, this is a little levitating chamber, we want to hang a magnet from the middle. So I have a little bit of string. And some scissors. Something about there will do. And what magnet should we levitate? These ones are pretty heavy. This one's too long. Maybe one of this one?
Let me see the fold.
I'm going to tie. I'm going to tie a knot around it. And I'm going to stick some other extra clay on it for make sure it really stays. And we'll put a little bit of clay. That where it should be. We have our little dowsing thing. We want it kind of in the middle. And we'll just wrap the string around this clay. Hopefully it's not too heavy. If it is, you know what we'll do? We'll add more clay. So that. All right, let's see how that does. It seems like it's staying, right? We'll put a little more clay on just in case. It's like tape, you know? Tape. Every science is we see what's working, see what's not.
You could probably use tape.
Yeah. You can use tape. You could probably use like small rubber bands and rub it around. All right, so it's moving a little. Just on its own because I was bumping it. Let's see if we can use our magical magnet wand. So this, you influence it. Ooh. Oh, I caught it. We'll stick to it. Maybe if I have two. Oh. I get it swinging back and forth. There we go. Hey, I got it.
It's like you're playing a game of table tennis by yourself.
Without touching anything. It's very quiet table tennis. Let's see what happens when we put it underneath. It might just break the pyramid. Ah.
Really want to pull down.
So I noticed the red side is pulling down. I wonder if I flip it. Oh, the blue side is pulling down. Very curious. And I can move it. Now this is not the wind. Oops. The magnets stick to everything. If I stop it, even if I blow on it, I'm not going to get it to move that much. So it's not the wind moving it, it's the magnets in our forces. Whoa! Let's see how I put it above. Oh, the red side's poking up. Flip it. Pink side, though. Blue side. I have to learn my colors. That's up. So making a levitating chamber like this is a pretty cool project. And again, you could do it with pencils and Play-Doh. And then you just need one magnet. Yeah. And you can come up with your own magic tricks that you can do around your magnet.
Your friends.
You can also attach it because there are 3 different kinds of magnets. So these magnets that I've been playing with so far are permanent magnets. Every time I pick this up out of the closet, it's going to be a magnet and stick to other magnets. There's also things that don't stick to each other, like these paper clips, but that do stick to magnets. So we call these temporary magnets. So they'll be magnetic, they will stick to magnets, but they don't stick to each other. Right? But I can attach. So these paper clips are temporary magnets. And look around what you got in your house, see if it's magnetic. So we have our penny from yesterday's science. Remember we were doing those hardness tests? Pennies are not magnetic. So not all metals are magnetic. They have to have some iron in it. Aluminum foil. Also not magnetic. It's usually things that have iron in them. So that's why the garage is usually a good place to find some magnets. So whatever you've got, oops, all those random screws and washers and bolts, see what is magnetic. So these brass things, not magnetic. These bolts are magnetic, they're just heavy. Oh. There we go. Some of them are too big. So you know how we can figure out what's magnetic? We can take a stronger magnet, swirl it around, and see what sticks. Those things are all magnetic. Those ones are magnetic. That's it. So these items have a bits of iron in them, and these items don't. Oh, did you see it swirl? Very interested in this magnet. The third type of magnets, I'm going to start to dismantle this. The third type of magnets are electromagnets. So electricity and magnets are pretty closely connected, and they're really the same force. They're just kind of opposite sides of the same force. So you can create magnets with electricity by winding wire and running a current through it. That will create a magnetic field. I'll clean that up later. That will create a magnetic field that works just like these magnets. And super-powered magnets, things like at the recycling dump, where they're picking up like cars with big magnets, those are usually magnets run by electricity. And then, so electricity can create magnets, but then magnets can also create electricity. Electric motors use magnets in order to run. So it's kind of two halves of the same thing. The electromagnetic forces work in both. And it all works because of what's inside of atoms. Here is a very simple picture of an atom. So atoms are made up of three things. They're made up of electrons, protons, and neutrons. The protons and the neutrons hang out in the center. And then the electrons spin around on the outside. So they don't just sit here. They spin around this way, and they're just orbiting all over the place. And the electrons usually hang out in pairs. So there's one on one side and one on the other, and they spin together. There's always one on either side, kind of like a seesaw. You want it to be balanced with one on each side. But some elements, including iron, have unpaired electrons. Just the electrons off doing their own thing. And because those electrons have a little bit of electric charge, a negative charge, they get unbalanced. They make the atom a little unbalanced, and to have a little bit of magnetic force. Now, one atom is not going to do much. But when you start getting a lot of atoms, all with their unbalanced, unpaired electrons in the same direction, then you get a magnet. And so these permanent magnets, the iron has had all of the iron atoms in this piece of iron have been aligned to go the same direction. And then because it's a permanent magnet, that stays. And so those atoms all stay in that same direction that we put them in. Something like temporary magnets, like this paperclip, when those atoms have the force of this magnet acting on them, they all stay in the same direction and they stay stuck. But then they kind of forget what they were doing when they get separated. And so they don't stay in that same line because they're kind of a soft magnet. They're going to move around again and not stay in that shape they're supposed to be. Any questions, John?
I have a question, actually.
Yes.
I feel like, as a person with jars of screws and such, that I like to have a magnet to pick them up. Not exactly how you did, in case I drop something. My question is more about using magnets. Sometimes I feel like when using a magnetic screwdriver, if I leave that bit on the magnet for a little bit, and then take it off, it retains its magnetism for a short amount of time before it stops being magnetic.
Yeah, some soft magnets you can kind of charge up to make into magnets. And good permanent magnets will remember that. Soft magnets will forget about it, but the more you charge them up, so the longer you left it with a real permanent magnet, the more it's going to remember. And that's a bit of a spoiler because at the end we're going to use a needle, which is kind of like a paperclip, only long and pointy. We're going to charge up a needle to make it into a temporary magnet that will work to make something pretty special. I'm not going to tell you what yet. Yes, they did yet.
Keep watching.
You're stuck here anyway, John, so everybody else has an option to leave.
Happy to be here.
So let's test to see. So I have a few different magnets, and one of the things you can test is how strong your magnet is. And so we need to design an experiment to see how strong our magnet is. And remember, in experiments, we only want to change one thing at a time. So I'm going to be testing with paper clips and just paper clips. I don't want to start with paper clips and then move to, things from my jar or move to some other random bits of metal that I have or the needles. I'm going to stay with paper clips, and it's something I can count because all the paper clips are the same size. So I can count how many paper clips I can make into a chain on my magnets. And the only thing I'm changing is the magnet. So let's try this one. We'll try the one we used in our levitating chamber. And maybe we'll try a round one, kind of an old-fashioned fridge magnet. All right. Which one should we do first, John?
Do the round one first.
The round one first. Okay.
Smallest to largest.
All right. So, it holds 1. Good job. It's a magnet. And now we're going to see how many we can make on a chain. We got 2. Oh. Oh. Well, we definitely got 2. So this one holds 2. Our results are 2. I want to put it where you can see 2. So it is a 2 paper clip strength magnet. Should we go from smallest to biggest then? All right. So, whoop, it's already got 2.
Oh, cheating and jump ahead.
It's like I could do that. That's no work.
Watch this. I've got this.
All right, stop wobbling. Steady hands. Holds 3. And I'm doing this the same way, is that I'm putting the paper clips end to end. I'm not sure I'm going to start doing them sideways or anything like that. Oh.
Won't want to do too much.
It might be. I don't want this magnet interfering, pulling things down. That's sabotage. Sabotage.
Wait your turn.
Oh, I think it's just going to stick with 3.
I really wanted to try before, but couldn't
quite
do it.
3 1/3 it could probably hold. All right, this one's got 1.
All right, here we go. Who's going to be the winner?
Hopefully, good thing I got lots of paper clips. 2, no problem. 3, can I get 4? I got 4.
You get past 4 though. That's the question.
Nah, it's like barely moving.
Or is the winner, looks like.
Yep, this one's the strongest at 4. Oh, I can try the wand. I didn't try the wand. This wand is kind of a mystery because it's encased in plastic. So I can't really see the magnet inside. Oh, we'll see. Get some more magnet, big clips. Now, the further the distance is, so it seems like the magnet's in the center. It's cheating on how we're connecting them.
How we're making this work. Play by the rules.
3. Nope. Doesn't look good. Oh.
Oh. It looks like it's going to be.
So it's 3. So it's the same as this one. Those ones are 3s. It wants to stick to the desk a lot. Do I have any others? I don't think so. So you can test the strength of your magnet. I also like the sandwich test. Is kind of fun if you have flat magnets. So these magnets make really strong sandwiches to each other. Really like to stick to the desk. There we go. Really strong sandwiches. So I'm going to use the tin foil to elevate it off the desk. Otherwise, it'll just stick to the desk. So, sandwiches. How many layers of felt can I fit? It will hold through 1 layer of felt. What's your prediction, John?
I'm going to go with 4 was the magic number. I think 4 again.
4, because 4 paper clips?
So the 4 paper clips. Yeah. That's my reason.
Okay. Let's see. And we'll hold 2. Connect through 2. About 3 layers of bacon. It holds 3. Will it hold through 4? Oh, it is, but it holds itself sideways. I'll still count it, right? Oh.
It's on the edge, though.
Let's test it again. Okay. Does that look good? Okay. Line up the felt right in the middle. Yeah, it'll hold 4. Let's see if it'll do 5.
It's going to be 5, and maybe I'm wrong.
Are you ever wrong? Okay. Nice and flat. 5.
5. I was wrong. 5.
And we'll do one more. It's 6. Oh, I thought I had it.
That's pretty close.
Give it one more chance.
Yeah, how are you going to pull that one?
Sometimes we don't remember when we did our science with the sound on Monday. We don't do just one test. Because maybe my hands go crooked or the felt is a little wobbly. We want to do fair tests, so we want to give it a few chances. Oh, it's like 5 3/4 of felt. Very nice. So you can devise your own experiments about the strength of your magnets and how many things you can chain or whether it will still magnetize with known distances in between. Fun to do. You can raid your fridges. Although fridges don't have many magnets anymore because they're all that plastic, stainless steel stuff that you can't stick magnets to. The age of refrigerator magnets is coming to a close.
I would caution those at home that happen to have a more powerful magnet. Be very careful of your fingers.
Yes.
You can get your fingers stuck. It does happen. It has happened to me. I have a story.
You have a story?
I'm allowed.
Is it family safe?
It is family safe.
All right. What happened?
We, in my field, in the IT field, for security, we use what's called the degauser, which is all it really is a very powerful electromagnet that erases hard drives.
Oh, so you use electromagnet.
Yes.
So those are the magnets where when you turn on the power, it's a magnet, but when it's off, it's not a magnet.
Yep.
Okay.
So we use those to erase hard drives.
Mm-hmm.
I'm not going to get into the science of that. It just does.
So does that mean our computers use magnets?
They do.
Oh.
Well, they did. It's actually less prevalent now, but that's a whole different story.
So if you have an old computer,
Correct.
It probably uses magnets.
Correct. But when using that degauser, it was so powerful you could not have any metal on you, like jewelry or a watch, or even metal in like your pants, like a zipper or a button. So you had to be very careful.
So it could pull the buttons off your shirt?
It could. It was very powerful. One of the things that you really had to be careful with, and we made a point is we would wear gloves. They were mesh, metal gloves, but not magnetic, obviously,
Uh-huh.
To protect your hands. That in the event that you turn this magnet on, and you happen to have a finger or something between the hard drive and the magnet, it could actually hurt your finger pretty bad.
Because like when you turn the magnet on, it would just...
It would instantly smush down.
So just like when I was making my sandwiches.
Just like
It was an instant smush.
So even a non-powerful magnet, if you're not paying attention, you might get a little bit of a squish on your finger, and that wouldn't feel very good. Just be careful. Go on.
That would hurt.
Yep.
Did that ever happen to you?
It happened to me once.
Do you still have all your fingers?
I still have all my fingers.
He does have all his fingers. And all his fingernails.
Nothing permanent.
Nothing permanent. I wonder how many paper clips that one would have held.
A lot of paper clips.
A lot of paper clips?
A lot of paper clips.
Do you still have one?
I do not.
No. Okay. We tested our magnets. So remember back when we had our pendulum that we had those two sides? We had the red side and the blue side. All magnets, even if they're not colored, have two different sides. It's usually called a north pole and a south pole, just like our globe has a north pole and a south pole. And so those two sides are not attracted to each other. So if I have it like, magnets really like to annoy each other too. So the north sides are not attracted to each other. In magnets, only the north side is only attracted to the south side. It won't pick up the north side, and it'll only pick up the south side. It has to be different, like opposites attract.
That's probably where the saying comes from, I would think, right?
Maybe. So likewise, if I take the south side is not attracted to the south side. It wants to be with a north side. You see that? Ooh. But it won't pick up this side. And the north side will only pick up the south side, but not another north side. And so that's true of all magnets. They have a field that they'll pick up. So this must be which side is it? South side. That's right, because the north side will only pick up the south side. Whereas this side, it won't pick up. So even if magnets aren't labeled, they do have a north side and a south side. So south won't pick up south. It will only pick up north. This one is the same orientation as that. And we can use that. And so that's why some sides don't want to pick up, and then some sides do. So you can also experiment with your magnets to figure out which is the north side and which is the south side. And you can kind of feel that. It's not going to show up on video because this is an invisible force, but you can feel that force. I can't get these to touch each other. There's an invisible force there. Now you can't tell if I'm just I could do this with pencils, but I can feel that force right there that's keeping me.
For yourself and you'll find it.
Yep, and even on little round magnets, there was a side that they want to be on. So these two, I can't perfectly stack. But if I flip it, then I can get a perfect stack. So even little tiny magnets have a north side and a south side. The only thing that's not a very good magnet is if you have, those free magnets you get from like the dentist or something, and they're kind of just this bendy magnetic stuff. It is a magnet. It does magnetize, but it doesn't have a very strong pole affiliation.
It's a very weak magnet.
It's a very weak magnet. It's just like a little bit of iron coated onto some rubber. So you need some other magnets. Like even these magnetic wands. We have one side that sticks and one side that does that. So that one's easy. This is what fuses. It won't cooperate, John. All right. And so we call it the North and South Pole. And in fact, the Earth is also a giant magnet. So its North Pole is also the North Pole of a magnet. And its South Pole is the South Pole. And the whole Earth is surrounded by a magnetic field that we can't feel, but we can see it. You know, you can see the Earth's magnetic field?
I did know that, actually.
Yeah? And where can you see it?
You can see it when usually up north,
Mm-hmm.
called the Aurora Borealis, or the Northern Lights.
The Northern Lights. So it's this bright green phenomenon in the sky. So the Earth, this is my biggest graphic yet.
Careful. Whoa. Big graphic.
Can we see most of the Earth? Hopefully you can still hear me with the microphone behind. So the Earth has layers. And at the center of the Earth is the Earth's core. And the Earth's core is mostly iron and nickel, which are two elements that have lots of those unpaired electrons. So they have lots of magnetic possibility. And the outer core is liquid because it's super, super, super hot. And the inner core is solid because that liquid is under so much pressure that it changes, it's actually a solid. And so the outer core, as it swirls around the solid inner core, creates a magnetic field. And that magnetic field is bigger than the Earth and kind of is a force field protecting the Earth from the solar winds and solar radiation. So when you see the aurora borealis, if you're ever lucky enough to see it, what you're seeing is actually solar winds and solar flares hitting the Earth's magnetic field and kind of being deflected. And that creates some energy. Remember, magnets and energy are connected, and it creates light. So here's a very dramatic picture of this in action. Looks like looks like the sun is coming to get this. This picture is not to scale. The sun is actually much, much, much bigger compared to the Earth. If the Earth was the size, of this balloon, then the sun would be the size of this building. And we're in Porosity Park. It's like 40 times in height compared. And it's also much further away. But this gives you an idea of how those forces are working. So the Earth's magnetic field coming out the North Pole and ending at the South Pole is going to protect the whole Earth, all in 360, all the way around. And then the solar flares are getting deflected off of the Earth. And so they kind of, like a ship going through the water, they're going to deflect it and carry it around the back. And the Earth is going to stay nice and protected inside. Now, the solar flares, besides just looking terrifying in this picture, are pretty bad for human life, for life as well. They have a lot of radiation, and that radiation would actually end life on our planet, and life wouldn't have been able to develop on our planet without our this electromagnetic sphere around us. Pretty cool. The magnetosphere, that's what they call it.
Very cool.
Very cool. And so we can only if you go up far enough north into like Canada or something, or if you go to Iceland or Russia or something, can you see the aurora borealis? And we can't really feel it. Some animals can. That's how they use kind of magnets in their brain to help them migrate. But we can create a tool, because us humans are good at creating tools, that will let us sense it. Do you know the name of this tool, Mr. John?
I think I have a hint at what it is, but I think I might not share it and let people figure it out.
Well, I'm going to show it to you.
Well, it's a compass.
I think the compass fell on the floor. It's a compass. So this is a pretty simple compass. And the way a compass works is it has a little needle in it, this little needle right here, where with a north side and a south side. And the south side is going to be attracted to the North Pole. So it is strong enough to sense the North Pole, that pull in the magnetosphere. And so if you hold it flat, then it will spin. I want to tilt it towards you, but you're not supposed to tilt it. It's supposed to be flat. It will spin, and it will find which direction is north. Now, what's interfering with this is the fact that this is a metal desk. Remember how my magnets stick to the desk so much? If I put it all the way down, it will just get confused by the metal desk. So we'll hold it up, and it's pointing that way is north. If I influence it with a stronger magnet, it will move around, but you can see how it is attracted to a magnet. So we're going to make a compass. So even if you don't have a compass, you can make your own. Just a few simple things. You could use a paper clip that you straighten out. I'm going to use a needle. You can use a pin. You could use a little bit of wire if you have some wire that's magnetic. You want to test whatever you're going to have and make sure it actually is magnetic. So this is magnetic. We're going to take our strongest magnet. When we tested it before, this was our strongest magnet. And we are going to kind of charge up this magnet, just like John told the story about how he left a drill bit in a magnetic drill and it kind of became a little bit magnetic. You can charge up these temporary magnets so that they have, so that they can act like permanent magnets for a little bit. And so what we're doing as we're charging is we're just going to go run along in the same direction. And what we're doing is we're taking all of those free floating unpaired electrons and we're coaxing them all to go one way. We're all going this way. Everybody point that way. And so we have to do this a bunch because there's a lot of atoms in this needle. We have to do it like 100 times. Have you been keeping count, Mr. John?
I lost count at about 20.
So you probably want to do this maybe about 100 times. Maybe we should put a timer on or something. I'm not counting. Have you been counting?
Jeopardy theme song.
I don't know. We don't want. It's going on YouTube. We don't want copyright problems.
Sure, we can't do that.
Because I'm sure my humming of the Jeopardy theme song will be very accurate. You know what the earliest compass was?
Earliest compass?
Mm-hmm. Who used
It would be something very similar to this. Maybe a needle and a cork.
No, the earliest compasses were from that naturally occurring mineral. You remember what it was?
Oh, I do remember now. And I think I did know this, but I forgot. Lodestone.
That happens. Lodestones, right. So lodestones are naturally occurring magnets. And so early peoples discovered that when attached to a bit of wax and floated in some water, that the lodestones would spin and would always point in the same direction. So that's an early form of navigation using lodestones. Most lodestones were a mineral called magnetite or a rock containing magnetite. And that was our mystery rock yesterday, remember? There it is. Did you learn how to use a compass? You know how to use a compass, John? Do you still remember?
I remember the basics of it, yes. I'm pretty sure I could navigate a plot of land if I needed to.
Do you need to?
Luckily, I have this thing called Google and GPS now that I don't like to need it.
I still like to have a compass in the car, though.
It's a nice thing.
Sometimes when you get turned around by Google and you're like, wait a minute, I'm trying to get to New York. Why am I going south? Not right. I don't know why I'm going so slow either. Deliberate. How many do you think that is?
2,000, I think.
It's not 2,000.
Yep.
If this wasn't live, we could do a little time lapse and it would be super fast. All right, let's try that. All right, I'm going to put all the other magnets away from my needle. And the next thing I need is a bottle cap.
Look, about it.
I need something that's going to float in water. So I used a bottle cap. You could use a cork, like John said. And then we need something to stick the needle to the bottle cap. I've got some clay still.
Oh, good old clay.
And we're going to smoosh the clay in the middle and then put my needle onto that. And then I just need some water.
In a bowl.
In a bowl. I guess I could do it in a beaker. I don't know.
What's much the trouble getting in the bowl?
Out the bowl. I'm going to fill this up like dangerously high so that hopefully we can see it pretty well. Dangerously high. What's going to happen? We're going to get wet. It'll be fine. All right, so hopefully my bottle cap floats. Yeah. Yep. Now, the problem we have, remember, is that the table is magnetic. So I should have done this first. I've got a really big book. It's the Dewey Decimal System.
That is a big book.
It's only the second half of it. All it has is like what is in every single section of the Dewey Decimal System. But I keep it because it's good to have a big book. So this will elevate it up off the table some more, away from that middle. And let's see if it's spinning. It's not spinning. I don't know if I did it enough, John.
pointing in the right direction.
Where's my real compass? Oh, it is moving itself a little. Oh, it's spinning itself back. That means it is doing something. Just needs a little time.
Just need a little patience.
I think it is. So can you see the compass?
I'm gonna move the camera.
You're gonna. Oh, we're gonna finish up with some special effects. I'm gonna reveal the mess of cables.
Cable very short. And,
Well, we don't have Zoom. And I can't tell if it's floating or if it's moving itself. North is like this way. So it was there. Now it's spun itself around again. But I can also tell that things are definitely magnetic. In fact, the compass itself might be interfering with it. So if you do this, you have to be very careful to be away from all things metal. Because just a little bit of magnet will influence it. You could just make yourself a little boat instead of a compass. I've drowned them all. Like all experiments, you try it. I didn't keep count. Maybe instead of 100, I need to do 200. Maybe you just play with your boat. All science is good. This is the last of our science, John. So,
it's been a fun week.
yeah, if you've missed any of them, they are all on our YouTube channel, which is at middletownnj.org/middletownmonth. Or if you search for it on YouTube, you'll find it. If you enjoyed hanging out with me and John, I am doing a craft program the first week of December. So each of those will be about the same time. They'll be 30 to 45 minutes. Simple things you have around your house, and we're going to do some different craft projects, a different project every day. That one is a sign-up event. So it's $20 per family or per computer screen that you want to watch it on. So that's going to, and it's 5 sessions, 30 to 45 minutes each. I think that ends it. It's kind of sad to be finishing this.
It's been a good week.
Oh, now that I've removed everything, it is back to the way it should be.
It just takes a little bit of interference, I think. Otherwise, I think it's a good book. Just doesn't do it.
So keep doing science, keep having fun. Get outside on this beautiful weekend. And if you have any questions, you can email us at recreation or come visit us at Forestry Park.
Thank you.
Bye.